Okay, yeah, this talk, I will talk about uranium-238. So the British has given a nice overview of isobars. So this is another nucleus, in fact, the first one which was collided and to show effects of shapes at relativistic energy. So I'm Giacalone from the University of Heidelberg, and actually one of the organizers. I'm not there. Very well, I will briefly recall what collective flow and nuclear structure and high energy nuclear physics are. So how you input nuclear structure to modeling of high energy nuclear collisions and how you see that essentially. And then I will discuss what we have learned basically from the uranium RAM, which was, the data was released about 7 years ago, actually almost 8 years ago. And what we learn about evidence of the intrinsic shapes from that data. And then I will talk about some prospects of exploiting more this data and even beyond this run, things that could be done in the future. So I'll quickly remind you then that high energy nuclear physics is a very big experimental effort of colliding essentially nuclei at the highest possible energies. This is done at the RIC and the LHC, the largest accelerators in the world. The idea is really to explore emergent phenomena and strong interaction matter, which are accessible in the regime, so that these accelerators can explore. And this is due to the energies, you can really study fundamental phenomena of emergence of state of matter from fundamental degrees of freedom. And this was a very successful program over the last 20 years. We have essentially become masters of making up effective descriptions of QCD, I would say. So this is the typical sketch of the evolution of heavy-ion collisions from the two colliding nuclei to the final distribution of particles going through a core-gluon plasma phase. And at each step, we essentially have come up with the effective descriptions of QCD for that particular stage. So you can start with two nuclei, let's say in the rest frame, and then once you look at them that are going to smash at ultra-realistic energies, they will look like this with some strong Lorentz boost effect. So we have an effective theory for the small x gluons, let's say the small x degrees of freedom that will populate this nuclei. This is the color class condensate. This will also give you some prescriptions to essentially go from time 0- to time 0+, and the subsequent state of matter, which is called the glasma in this effective description. This is a very important thing actually, because it gives us some insights about how the energy can be deposited right after the collision, which is crucial to start modeling. And then there is a particle description which sets in, another effective description of QCD, which is about the transport of the created matter and how this approach is finally a sort of hydrodynamic, equilibrated medium, which is then described by an emergent equation of state, an emergent pressure gradient force, and transport coefficients. So heavy-ion collisions is essentially a tower of the effective theories of QCD, and I think what we want to achieve in this program and what you're now able to do is to put the next ingredient of this cartoon, which is the time equals 0, or time equal -infinity, which is using also effective theories of QCD for spatial distribution of the large x degrees of freedom, which essentially are nucleons. And so this is why we want to refine the picture by having more refined input from nuclear structure and in a phenomenologically driven way. So you have to reconstruct the initial condition to go back to the, let's say, from this stage that you observed to this one. You have to be able to somehow go back in time, and this we can do. Now this has been discussed extensively in the program. We only see particles, but we want to reconstruct the QGP inside. We have to study how the bulk of particles are distributed, like Pre-Twitch was showing. So we study how explosive the expansion is, I mean the PP of the particles, and how whether the distribution of particles is anisotropic or not. And we extract this coefficient of anisotropy, which is called anisotropic flow coefficients, which tells you whether you have modulations in this particle distribution. And from these measurements, you can actually reconstruct your initial state. So these again, we are masters at doing that. We can do this very precisely. Just to give you some insights, this is something which is really inherent to the emergent hydrodynamic description. The expansion is essentially a deterministic thing, if you want, such that you have very, very precise relations between what happens at the beginning and what you have at the beginning and what happens in the end. If you have collisions with the same number of particles, like the isobars discussed before, but you put them in different volumes, this is exactly what Pre-Twitch was discussing. The one with the smallest volume will flow strongly, so larger mean PT of the final state hadrons. The one with the larger volume will flow less strongly, so less mean PT. If you have something which is anisotropic at the beginning, you will have imbalance of pressure gradient forces, and final state anisotropy in momentum space. So an ellipse in the initial state leads to an ellipse in momentum space. A triangle leads to a triangle, and so on. Now you observe something like this, and then you reconstruct the initial condition. So shape and size of QGP by this technique can be reconstructed from data, and this is basically the starting point of all our discussions. Now the question is, you need to model then the shape and the size of the QGP and what happens in the collision process, and this is where you have to start from nuclear structure essentially. The QGP must start from an input from how you really take your two nuclei that are colliding on an event-by-event basis. And what we have understood from the phenomenology, let's say a very successful theory to data comparisons in the last 20 years, is that the picture is essentially like this. And what happens is that, so the scattering occurs mainly within nucleons, and the destruction of the two nuclei in the interaction process makes that there is a sort of quantum measurement of the nucleon positions in the interaction regions. So I like to show this picture, which is taken from my colleagues at the Physics Institute in Heidelberg, where they do ultra cold atom experiments with few particles, and they're actually able to image the wave functions by basically make them collapse. And so what you understand is that something similar happens in the interaction region of heavy-ion collisions, where you sort of localize everything which is inside the colliding nuclei, and so you define interaction regions from that. And then with this insight, of course, you have to start from some distributions of nucleons. The simplest one is, of course, just a mean field description, essentially, which is good for a system like Lead-208, where you simplify the full problem into a problem of independent particle living in a sort of spherical bag, which is phenomenologically something which is very accurately described by Woods-Saxon density profile, the one which British was describing. And this is your, say, first-order model, zeroth-order model of a nucleus. Just a Woods-Saxon bag with independent particles, which is, in fact, realistic for a system like Lead-208. Can, of course, be improved. This is all the business of energy density conventional theory, where you try to get this potential from effective nucleon-nucleon interactions. But let's just start with this, which is what we've been doing for many, many years in heavy-ion collision. So you use your Woods-Saxon as a density of nucleons. This is what is called the Glauber-Monte Carlo approach. This is what everyone does. You sample your nucleus inside your two nuclei, and then you get an interaction region which will look something like this. This is one configuration in one event. And then you have some phenomenological prescriptions. These are sort of very accurate at phenomenological level, and I guess you can also get some insights from high energy UCD from this, about how you should combine the two nuclei to get an initial energy density. And this is also something which I sort of infer from the experimental measurements. But once you have done this, and you are able to define a profile for your Coulomb plasma, and then you propagate to the final state, and you look again at these anisotropic coefficients, which result from the expansion, which will be in this phase, you can get very accurate description of the measurements. These red points are IPW plus European simulations in 2020. And this is these points are Alice data. So this is a very, very precise description, which essentially justifying, if you want, the way this is modeled. And it's the art is really a mean field description of the lead nucleus, which is making this possible, plus some ingredients that you can essentially check in your data. So the idea is then that once you go beyond Lead-208, you start to dealing with very strongly correlated systems, which is very typical in nuclei. Then you have to take into account spatial correlations of nucleons. And energy nuclear physics tells you that, yes, you can do that in a convenient way by use of intrinsic shapes. So you can still use your one-body density description with independent particles, but you have to deform the potential. And this is the way to go if you want to see this. So the idea is that then a collision is basically something where you have something deformed and oriented randomly, and once the nuclei interact, there is a sort of selection of one orientation. You actually see that, and the nucleon will be distributed according to something randomly oriented and deformed. And this is how you would then have a manifestation of these shapes in a high energy collision. And so while these intrinsic shapes are not something which, let's say, something you can directly observe, that they are everywhere in nuclear phenomenology, and so it makes sense that they show up as well at high energy. The way you implement that is then to modify your your Woods-Saxon profile with something which is deformed. This is the most standard, I would say, expansion. And then we can ask the question of whether in the hydrodynamic model of heavy-ion collisions that we have constrained from, for instance, lead-lead collisions, you can actually consistently understand the signatures of these shapes in high energy data. And this is, I think, it's a very important goal to ensure that what you're doing makes sense, in the sense that you can vary nuclei and nothing bad happens. Your description is consistently correct in a sense. And so then then uranium-238 comes in. So to see these effects, this is actually a very good nucleus because this is sort of archetype of a well-deformed nucleus. Beta 2 of 0.29, so something very deformed from the spectroscopic data. Uranium-uranium collisions are available at TRIC, and this is really an ideal system to it. It's a nucleus, if you want, that at the mean field level actually is already well deformed, and so it presents a excitation spectrum with fully fledged rotational bands. So this is really, the archetype of a deformed nucleus, and you want to see if you can understand the phenomenology of its shape and his manifestation in high energy data. So is it there, and do we understand it? Okay, and this was the first effectively evidence of nuclear deformation in high energy nuclear collisions. So the elliptic flow that you see in the final state is a contribution from some reaction, typically some reaction plane flow, which is just given by the almond shape, the elliptical shape of the overlap area, and some fluctuation, which is typically, again, driven by the nucleon positions. It's something which I understood very well. And it means that this fluctuation scales like 1/8. This is how this was discovered, actually, by comparing copper-copper and gold-gold data. In central collision, this was much bigger in copper-copper because of the smaller nucleon number, actually. So what happened when STAR showed their data is that there was, in fact, a breaking of the scaling, so a sort of anomalous enhancement of V2 in central uranium-uranium collisions, so which in principle should not be there if you're just dominated by the nucleon number. And in fact, you can also see some realistic AMPT simulations of the process where you take spherical gold and spherical uranium, that in fact, uranium is below gold for the same observable if you don't take deformation into account. So, which is how it is, it should be. Now, if you start adding in your beta deformation parameter, you start to lift this, and this is what is also observed experimentally. So deformation essentially naturally explains what is observed here, so this sort of anomalous enhancement of V2 in uranium-uranium collisions. So I would like to show now a calculation which shows how this enhancement actually works. It's a very simple model, but I think it's insightful actually. If you take a very simple model of the nucleus, like a Gaussian in 3 dimensions with some deformations, which you can do, then you can define, then you can rotate it randomly and let's say project it over the plane. So like boosting it at high energy after a random orientation, you get some thickness function, which is in fact a linear function of the deformation. And then if you take 2 such nuclei and define an energy density in some ansatz, which is similar to what is done in the phenomenology, then you can define eccentricity, for instance, which would be the seed of the final state anisotropy, and average over Euler angles to get the mean squared anisotropy that you expect in the final state. And this is in fact just a function of beta 2 squared with a coefficient in front. So it's actually proportional to beta 2 squared. So you expect a correction proportional to beta 2 squared. You can also see this can also be derived in other ways, like Zheng Yong did 2 years ago. But this is a model which is similar, for instance, to what is done in actual phenological models. And so the correction is really quadratic in beta 2. Now we can look again at the anisotropy as a function of beta 2. This can be done in models, for instance, collisions at b equals 0. This is the elliptic anisotropy of the system. It's a quadratic function of beta 2. This was also verified again in AMPT with, the initial state eccentricity and the final state elliptic flow. They are all linear functions of beta 2. And in fact, these extends as well to higher centralities, meaning that you can just add in the reaction plane flow. This is just a shift, basically, but this is still a quadratic dependence on beta squared. And this is what is observed at RIC, essentially. Now, if you say, okay, this is the correction, how well can I understand RIC data? Well, let's do some state-of-the-art calculations, which have been available, I would say, become very quantitative in the last 5 years or so. You can try to do estimates of how much the V2 would be from the initial state anisotropy with some linear scaling, for instance, something realistic. You get something like this from gold to uranium. There are also epiglasma plus music simulations of uranium and gold data, collisions, where they implement, again, realistic values of the deformations. And in fact, something interesting happens is that the splitting that you get between uranium and gold collisions is way too large than what is actually observed by STAR. Meaning that there's something not very nice going on at the level of how you implement this deformation, probably, because the splitting is just overestimated. This is actually observed in other papers. In fact, this connects me with the seminar of Vitek Natsarevic from the one, the first day, that there's been for 20 years an improper implementation of the deformation in this Evian collision, because what we want to parameterize is essentially the shape, the intrinsic shape of the nucleons. And what has been done is that the deformation parameters that you put in your Woods-Saxon profile are just taken from basically tabulated data from the multiple moments, but these two are not the same thing. So this can be a small difference, but it's something which is actually enhanced whenever you have both a large quadrupole and an hexadecapole moment in your nucleus. And this is precisely the case for uranium-238, because it's both a large beta-2 and a sizable beta-4. In fact, if you can write down some formulas and try to see what is the difference between these two, essentially. And the leading order correction is essentially, there's a correction in beta-2 squared, but also in beta-2 times beta-4. So as soon as you have some beta-4 and a large beta-2, this becomes important. And for uranium-238, this correction has not been taken into account. So you can see this more directly in actually energy density function calculations, where you like we did here, 21 different Kerme functionals, which gives you some deformation for the uranium. This will be the experimental value, right? The one to compare with the B2 from low energy experiments. So you can actually capture that. This is what we measure for, what we calculate for beta-2 uranium. So 21 values, which are essentially all on top of each other. But if you then try to see what would be the shape of the Wood-Saxon distribution, which fits your one-body density, return that these calculations is actually reduced quite significantly to 0.25. And this is actually the value that should be implemented in hydro simulations. So we're redoing these calculations, this work in preparation. And if you go from 29 to 25, then you are much closer, or I would say compatible now with what is measured by STAR. This I'm just really zooming in the most central events where the deformations are most important. So this means that you have effectively to take the density of nucleons or the Wood-Saxon from consistently from an energy density function calculation, for instance, something which really tell you what the shape, what the intrinsic shape is. You should not take just experimental tabulated parameters, and this is something important for well-deformed ions, something very obvious for low energy physics, but we figured this out actually now. And there's a very, yes.
Can I ask a question? So I start asking question. If you have a density functional calculation, can you just fit that to get the beta-2 and just use that in the Wood-Saxon again, or this is not enough? You have to use the actual DFT.
In this case, for instance, sorry, I should say that the way we got this is precisely by computing the one-body density from the energy density function calculation, the mean field calculation, and then you fit a Wood-Saxon in 3 dimensions, and then you get the resulting beta parameters, and that's the right intrinsic shape to use.
Okay, so we can still use the Wood-Saxon parameterization. Just need to modify the.
You have to fit the energy density function result.
Right. What that means is that beta-2 is still consistent with the portable, the E2 measurement, because
the measured one. Yes.
The body distribution.
If you compute the multiple moment, you will get the right number.
Okay.
Very well. And then the other thing so this is important, going to more exclusive things. Then there has been always the question whether we can discern tip-tip and body-body collisions, which essentially look at this. This was also discussed by Pritwish. In fact, this was one of the motivations, I believe, for the uranium-uranium run, which you should be able to distinguish between these two, because this should produce more multiplicity than this one. If there is an N-call scaling which underlies the particle production, but actually this was not really supported by data. For instance, it was showed in this paper that this scaling predicts something which is not consistent with what is observed. So the scale is more probably like N part, which is in fact consistent with the models we use today. Now, so how do you discern these two phenomenologically? So the right way is shape-size correlations, or let's say one simple way is shape-size correlations, which is precisely what Pritwish was discussing, that a collision like this leads to a small circular area, whereas a collision like this leads to a larger elliptical area. And so essentially, when you looked at the central collisions, ellipticity of the QGP is positively correlated with its area. So large ellipticity means also large area. But at the same time, large area means less density in your system, and so the particles will flow less, so smaller mean PT. In fact, there is a negative correlation between V2 and the mean PT. So in fact, there is the simplest measurement you can think of is what was, so actually I have just a picture to illustrate this essentially. If you do a body-body collision fully head-on, and the tip-tip collision fully head-on, like this and this. So in this case, you create a circular covalent plasma. This is from a realistic simulation, if you want. In this case, it's very elliptical. The LB flow can be larger by a factor 3. The mean transfer momentum can also be larger by 10% in this case. So this is more denser than this one. And this is, so more density, less anisotropy, more anisotropy, less density. You can play between mean PT and V2 to see this effect at play. And the simplest measurement you can think of is something that was done by STAR actually 2 years ago. tortuoso, where you say, let's go to ultra-central collisions where I'm mixing these configurations. And then I look at those, I sort them in explosiveness, so from the large mean PT of particles to the small mean PT of particles. And then I should gradually see a transition from this overlap, this geometry of overlap, which leads to a dense system, but circular, to this overlap, which is elliptical and less dense. And then in fact, they could see even on top of huge fluctuations, which are associated with the fact that you measure mean PT on event by event basis in a finite sample of particles. This negative slope, was still visible. So as you move from large density to small density, they could see the V2 increasing, which is basically the fact that you're isolating these body-body configurations, which is you sort of see by eye in this plot, in a sense. And this does not occur, of course, for gold, because there's no strong deformation there. So you're sort of selecting here visually body-body and tip-tip. I mean, this is the underlying physics. I would like to then present another simple model calculation of this phenomenon, just to give you more insights. This is something again was done by Giacalone a couple of years ago, but we use again here a sort of realistic ansatz where you have again Gaussian nuclei, a thickness function of something which is randomly oriented, then an energy deposition ansatz of this kind. Then we compute the eccentricity, but also some predictor for the mean PT. The total energy of the system is actually works pretty well. Then you can compute the covariance of the Vn and the mean PT, so V2 squared and mean PT in like this. And this actually turns out to be proportional to beta 2 cube. And there's also leading proportionality to gamma, the triaxiality actually. But there is a minus sign, and this is very interesting. This means that precisely this negative slope, you can see it as coming from this minus sign. And so you can actually measure this covariance experimentally. This was the correlator proposed by Piotr Boczek. It's the covariance of V2 and mean PT, normalized in some way. And again, do you see then the manifestation of this negative contribution, which comes from the beta 2 cube? And so if you compare then preliminary star data of gold and uranium, you can see that as you go to the limit of ultracentral collisions, very high multiplicities, this turns to something negative, which is precisely the manifestation of this negative sign. So the effect of the shape is just, again, you also see it by eye in this plot. And you can do hydro simulations, again, IP last one plus music, with different beta 2 parameters for the uranium. And again, you see the same transitions from positive to negative. Overall, these simulations for the moment are not giving a very good description of the data, but this is something that has to be improved in future, I would say. Then we will understand even better if we get consistently this observable with the deformations that we expect. So this is again telling you that you really see the interplay of these body-body and tip-tip collisions in your experiment. So this is essentially what we have achieved from uranium collisions. We have seen for the first time the enhancement of V2 squared from a deformation. This is a quadratic correction like this. Now we have understood that whenever you collide nuclei that are deformed or significantly deformed, you should be very careful and take the input from energy density functional. You should not read out some data, the deformation parameter from data tables, from the energy data, and just put that in the Wood-Saxon. This is especially important for uranium because it has a sizable beta 4s, and we see this beta 4 essentially in the high energy data. Its effect is to reduce this beta 2 Wood-Saxon. is very interesting. So the optimal input infrastructure, I recall here what was said by Benjamin Bali on the first week, is you compute a one body density consistently from the mean field solutions, and then if you want to use a Wood-Saxon, you have to fit that, and this would be fully consistent with low energy theory. And then what we have learned is that mean PT in conjunction with V2 allows you to discern body-body and tip-tip collisions, and this led to very dramatic manifestations of negative values of V2 mean PT correlations in central uranium collisions. And very good. So if I still have time, then I would like to say, well, what extra we can do with this system, which is again archetype well-deformed nucleus. We want to understand this very well, because then we can understand the other nuclei for sure. So I've discussed beta 2, beta 4, which we see many things, but there are still things in the intrinsic shape which would be nice to see, like the octupole, the triaxiality maybe, these are not so much about, and the skin. And this, we are in condition of looking into these things, and let me just say a few words. So the quadrupole deformation was V2. The octupole deformation then will be V3, triangular anisotropy. This is just a fluctuation. There's no, if you collide two ellipsoids, you don't generate an intrinsic triangularity in your system, okay? So this is just a fluctuation from the nuclear number, which is scale like 1/8. This is again very, very solid. But If you go to uranium-uranium and gold-gold collisions, again, limit of 0% centrality, fully overlapping systems. In fact, uranium-uranium has a larger V3 than gold-gold. It's actually very significant, and it can be measured precisely. Once again, this is breaking the 1/A scaling. You should not see this. If I do IMPT calculations where I just do gold-gold and uranium with whatever deformation, I will always see a larger V3 to V3 squared for gold-gold than for uranium-uranium in the limit of central collisions. So this is breaking again the scaling, which we expect from the 1/the number of nucleons. And is this because of some octopole deformation? So the octopole deformation is a bit tricky because you will never get it at mean field level, so you have to do beyond mean field calculations, but luckily people these days can do that quite easily. So this was the seminar by Tomás Rodríguez. If you construct, like in the projected generated coordinate method, wave function from consistently constructed from mean field solutions, then you can you go beyond mean field and see the octopole arising. This is the way you should do it. So if you try to study beta 3 at the mean field level, you see typically something which is peaked at 0. So this is a beta 2 beta 3 correlation. Uranium is very deformed in beta 2, but at mean field level at 0 beta 3. Now if you do this procedure and then you compute what is called the collective wave function after projection, which is basically something which gives you insights on the distribution of the deformations, or how important these weights, depending on Q, which is the deformation parameter, essentially is in your system. Then for the ground state, you see that actually the minimum in beta 3 shifts. The important weights are for beta 3 of about 0.1, and this is actually very sharply peaked here. And then this means that, in fact, the configuration, which is most important after you include this correlation more sophisticated, is in fact a pear-shaped configuration. And this is the one. Then you should do, again, your mean field calculation constrained at these deformations, and you will have some shape like this. And this is the one that you are in principle supposed to use in the high energy collisions, or the one which will capture most effectively the spatial correlations of nucleons. And do we see then, does this explain some big data? So there will be, again, an enhancement of the fluctuation of V3 by some beta 3 squared. This is always squared in the deformation parameter. And we did I just did some trend to calculation starting from precisely the shape that the nuclear structure here is giving. So Luis Robledo and Tomás Rodríguez. The beta 3 Wood-Saxon is actually about 0.08. So it's very significant, I would say. And if you do then simulations with uranium-uranium without an octopole deformation and gold-gold, then you see that gold is above the uranium, as expected from the 1/A scaling. As you add this parameter in, you see something which is very close to gold at the both central collisions, and then it's consistently above the gold-gold results. And if I show you again the start data, they saw something which looks exactly like that. So if I just take this model calculation, then assume that I can propagate the eccentricities to the triangularities, and that the response coefficient doesn't change between systems, then I will conclude that Rick has actually observed a beta 3 Wood-Saxon of about this magnitude in their data. I can consistently describe the V3 squared that they see, and now it changes between gold-gold and uranium-uranium collision from the pear-shaped 230 uranium. So this we will do, I guess, hydro simulations to verify this relation, but this seems really, really solid, actually. So I would say Rick has observed pear-shaped uranium, and that's very exciting. So octopole is one thing. Now, if you move to off-central collisions, where deformation becomes less important, actually, and you are more sensitive to skin effects, like what was also told by Pritwish. In fact, it's very interesting that if we use now an appropriate uranium for uranium-uranium collisions, and we try to compare to star data, we get a nice description in, okay, these are always IP plasma plus music simulations. We describe actually quite well central collisions, but then the centrality dependence is a little off. You see that we don't really get the ratio UU versus UAU. In fact, this, if you look just at individual systems, you can see that it's an issue coming from uranium-uranium collisions. This means that there's something in the centrality dependence of V2 of U plus U, which is not captured by the hydrodynamic model. So this can be an issue with the IP plasma ansatz for the energy deposition, but this, I would say, it's maybe unlikely. Otherwise, there could be some issue actually with the skin of 230 uranium. So there was actually some very recent studies showing that the skin of this nucleus in energy density functional calculations is not at all constant across the surface, but depends on the polar angle essentially. So this, I think in practice, this means that like a body-body collision actually sees a larger skin than a tip-tip collision or something like this. And so while they only studied in these papers the spectator numbers, it will be simple to see what this does on the eccentricities. This is hopefully something which you can do.
So I have a question here.
Yes.
Are there any evidence from a low energy experiment to show that neutron skin depends on when you have a deformed system? The neutron skin actually depends on the angle, like anisotropy in the neutron skin. Are there any experimental evidence for that?
I personally, I don't know if someone else can answer.
We do have a answer.
Yeah, I can comment. I think in the low energy or let's say intermediate energy estimates, the way we derive the neutron skin, the nucleus is approaching the target in all orientations. So there is no way that we would have a preferred orientation. So basically an integration over all angle average.
Okay.
Yeah, so yeah, very good. So in fact, since here we are actually able to see somehow the effect of body-body versus tip-tip, I would say that this effect can in principle impact the data. So this has to be studied. So, and actually this connects in my opinion, so if you can go on what has been done recently again by STAR, which will be presented by Daniel Brandenburg in the final week of the program, which is the actually measurements of the neutron skin of gold and uranium in high energy. So the process that they said here is...
you have 5 minutes.
Okay, very good. Thank you very much. So is photon nucleus, ultra-peripheral collisions and production of rho zeros, and then reconstructed from pions. They can measure basically a distribution of the momentum of the rho zero, and which contains what they call a coherent component, which is basically coming from the gluon density in the nuclei. So this I guess we discussed this more in the program. They can actually then make models for the gluon density and see whether they can get a fit of data and what parameters essentially for the gluon density they will get. So for gold, they actually measure a value of the neutron skin then from, again, some Saxon fit of 0.17 Fermi with some error. This is fully consistent with, I would say, low energy theory. Actually, we put online a paper last month about state-of-the-art results for gold, and we get the same number actually for the neutron skin. So this means that this method seems to be actually very reasonable. But as they go to uranium, so the same observable, some kind of fit of the same type, actually they measured 0.44 Fermi for the neutron skin. Sorry, I forgot the unit here, which is not longer consistent with what low energy physics predicts. So this is once again I believe, some manifestation of the deformation of the uranium, which is biasing this result. And I don't know yet exactly how that enters in the way this is modeled, and I will be very interested in figuring this out. Yeah, maybe during the program. So there seems to be maybe 2 different instances where the skin is maybe not properly working in the way we implement it, and it would be very exciting to make progress. So in uranium once again seems to be the right system to do this. So last, okay, just few thoughts. Triaxiality of uranium is going to be very hard. Triaxiality effect exists. Again, you have to go beyond main field, but some calculations were done, and it turns out that gamma is about like between 5 and 10 degrees. I think that's also what you would get at the level of the Wood-Saxon. So how can you see a triaxiality of 7 degrees or something like that? Well, the point is, I think it's possible, but will require very quantitative comparisons in the sense that we have these observables now, like the V2 min PT correlation discussed before, which has a leading dependence on cos 3 gamma, or what is called the skewness of the min PT, so the third moment of the min PT distributions at a given multiplicity, which is also sensitive at a leading sensitivity to cos 3 gamma. And there is a beta 2 cube in front, which means that it's not impossible that the small effect is actually amplified. And hopefully we will get so quantitative in the comparisons that we will also be able to accept this gamma. Otherwise, I think this analysis in general to see what the shape does and whether you can consistently understand the signatures will be very interesting to do also at different energies. For instance, once you go to very low energy, where you have to do different kind of simulations with the full 3+1D dynamics implemented, it will be good to again look at spherical and very deformed systems to see what the shape does and whether you can consistently understand then also with what you know from high energy. I would say small X evolution is something that can be studied, can also be studied maybe at the EIC in future. Uranium may not be the best collisions to do that, or uranium as a nucleus. So this was actually presented by Pragya last week. It was very nice. How the anisotropy of the region of overlap changes as you increase the square root of S, essentially, just because of small x evolution that you can model in high energy QCD. Effects are small, but there are some effects, and it's worth investigating this further. The final comment then is going, let's say, away from uranium, but I mean, the lesson I think from uranium is that then this idea of having nuclei which are well deformed with rotational bands is something that would be also very interesting to study in the context of small systems, where you want to understand better where the flow is originating from. And so we have nowadays ab initio calculations we discussed next week of the program, where they can actually provide very good description of the experimental data on these rotational bands, and so we can get very precise input about the shape of this nuclei. So this is the best example, the 20 neon. And we also will have a baseline of oxygen-oxygen collision, which should be way more spherical nuclei. And so this will give us, this is essentially something that could be collided as a means to really stress test the origin of collectivity and the response to initial geometry in a small system. So it's like going from uranium and gold. You divide by 10 the mass number, and you do neon versus oxygen. It's going to be it's the same mass ratio actually. So and we are actually doing with some works on this will be out shortly. So I think this is my last slide actually. Yes. So I will just summarize. I think it's very exciting that we can now very confidently say that multi-nuclear correlations in nuclei leave an imprint in multi-particle correlation in the fast of the core gluon plasma, and we want to understand everything consistently. So initial geometry and collective flow of energy nuclear collisions strongly impacted by nuclear deformations, and uranium collisions were the first systems that were proposed, the first that were collided, and the first where we observed the effect of the nuclear shape. And we are getting, I think, to the place where we understand consistently all these observations, which eventually gives us much confidence about our understanding in the collision progress and process. And so there was a lot of progress made, and I think we can make more. So octupole and understanding octupole, so deformations beyond mean field, and the skin will be next. And then let's say what we have learned from these very large systems can be, I think, them also applied to smaller systems and also lower energies to see if the technology remains consistent. So I hope you find this interesting, and thank you for listening.
Thank you, Giacalone.
Yeah, thanks, Julian. Can you hear me?
Yes, I can hear you.
Great. So slide 35, this measurement, I understand, is sensitive to the gluon distribution. So I wonder why it's interpreted as a neutron skin, because I would understand it just as, the nucleus growing with energy by, Revo diffusion or something like that. And that's the gluon distribution. I have no idea if these come from protons or neutrons. So why is it interpreted as the neutron skin being larger, not just the whole thing being larger?
Well, what you get here is basically the matter density, okay? And then what you assume is that you know the proton one, and then you can derive the neutron skin, the neutron density. Essentially, this is an estimate of the neutron, I would say the
That's a direct response by Giacalone.
Yeah.
Yeah, so if that argument is correct, then the goal is also see bigger, but we didn't see it. So that argument said the size actually grows with the energy to apply to the goal ions as well, but we didn't see it. I mean, he basically said the goal is actually exactly the same as the calculation, but the uranium somehow is bigger. So I don't think it's due to the growth of the nuclear size as a function of energy.
Yeah, and maybe I can comment on this. What was the second thing I wanted to say? I think there's no evidence at all that nuclei become particularly big, at least in processes mediated by gluons in our collisions. And I believe that, in fact, once you extract these parameters, you're very close to the point-like density. So this is at least how I understand the VI collisions, that it's really the point-like density that matters.
Okay, Uli?
Yeah, Giuliano, I found your claim of a pear-shaped uranium nucleus provocative, especially after listening for 2 weeks here to nuclear structure theorists who warned us very strongly not to interpret these plots that you're showing here in the way that you take the minimum and then you just take that as the deformation of the nucleus. This is a little bit like you would take the single particle density distribution for lead and replace the nucleon position by the RMS for all the nucleons rather than for the distribution. I think we have to start thinking about these things probabilistically. That means that because what collides is an energy eigenstate of the uranium or whatever nucleus, but what you are trying to measure is a distribution of positions. And as you know, that in an energy eigenstate, the outcome of a position measurement is always uncertain. It's always characterized by quantum fluctuations. And while we know very well and have learned to implement this for the nucleon positions, the radii, we have to do the same thing also for the nuclear orientations, I think. And I don't see anybody doing that yet.
Okay, thanks for the comment. I guess this is the most convenient way of trying to encapsulate these correlations in your model. And you can see how far you can go with that, and then we can try to make it better.
Yes. Bill?
Yeah, what happens to these both peripheral collisions to the target for Giacalone? You've been talking a lot about the multiplicity, right? But my question is, what happens to the remainder of the system?
Sorry, can you repeat the question? I couldn't understand the first part.
What happens to the spectators? You're talking about the participating part, right?
Yes, I'm definitely talking only about whatever the matter is created in the center. But indeed, they can measure as well the spectators, and they can actually measure it, I would say, with some precision. And I don't think we have discussed much so far what you will learn from that, although there are like recent papers also by Giacalone where they again say maybe we can use them to constrain further the skin, for instance, in the limit of ultracentral collisions. This sounds very reasonable. So the spectators, someone can correct me, but I think they are detected with a certain level of confidence. I think it's not a perfect measurement, but you can probably do something with that. I would say we have not done much for the moment.
Yeah, I'm quick saying, if you can capture all the spectators, that would be great because you can determine centrality and also independently all the structure information. But we don't have this capability. Yeah, John.
So in one of the slides, I don't remember, you compare the IP plasma with different deformation for the uranium as a function of centrality, and so there may be issues with the skin. Maybe
it was this one. Yes.
Yes. So if you then use the neutron skin, at least assume from the UTC measurement, much bigger skin, will that match this data?
That's a nice question, but I didn't try. Okay. If you increase the neutron skin, you should make your V2 grow less as a function of centrality. So qualitatively, in fact, the effect would be the same. But I should try a calculation. Qualitatively, it will be, if you should go in the right direction.
Yeah, the idea is to see if these two measurements are consistent, right? At least whether it's right or wrong, it's a different issue, but whether they can be consistent.
Yes.
That's a good point. Thanks.
One last question.
It's not a question, it was a comment to the earlier questions about measuring the spectators. We do measure the spectators with our theoretic calorimeters, but the information, the distribution or the shape is lost. We just get like two clusters on both sides. So from the shape of, it's hard to reconstruct the shape of the spectators from what we measure. We don't have a detector like that.
Actually, the V1 does carry some of the deformation information.
That, yeah, would be something complicated, yeah. So